Last chapter, we gathered the ingredients: the half-second round trip, the reference point that splits the timing in two, and the SIB19 fields your phone reads straight off the satellite. Today we assemble them. This is the full timing advance formula for NTN. How your phone combines its own GNSS calculation with the network's common delay. Why a value called K-offset even has to exist. What Kmac quietly keeps in sync, and how your uplink stays locked onto a satellite moving through space. In terrestrial 5G, timing advance is simple. The network measures how late your signal arrives and sends back a small correction. That closed loop can't work over geostationary orbit. By the time a correction came back, half a second has passed and the geometry has already moved. So NTN flips the model. Instead of waiting to be corrected, the phone pre-computes almost all of its timing advance ahead of time. The full value has 4 parts. The first, and the biggest, is the UE-specific term. This is the service link delay, the phone-to-satellite half, that the phone calculates itself from its GNSS position and the satellite's ephemeris. The second is the common term NTA common, signaled by the network in SIB19. That is the feeder half, from the reference point down to the G-node B. The third is a small closed-loop term, still refined by the usual timing commands, but now it only has to trim tiny residual errors. And the fourth is a fixed offset, the same constant used on the ground. Add them together, scale by the system time unit, and that is your total timing advance. Let's zoom in on that common term, because it hides something clever. The feeder link runs from the reference point down to the gateway and the G-node B. On a geostationary bird, it barely moves, but on lower orbits, that distance changes constantly, so its delay is not a fixed number. The network can't broadcast a fresh SIB19 every few milliseconds. So instead, to common comes with a drift rate. The phone takes the common value at the epoch time, then extrapolates it forward using that drift, moment by moment, until the next update arrives. It is the same trick the phone uses for its own half. Ephemeris plus GNSS give a position now, and the known orbital motion predicts where things will be seconds later. Between broadcasts, the phone is not guessing, it is running the physics. Now the part that trips everyone up. K-offset. 5G scheduling works by relationships. The network sends a grant in one slot and says, transmit your uplink a fixed number of slots later. On the ground, that gap is a handful of slots, a millisecond or two. Now drop in the satellite. Your phone has to advance its transmission by the full timing advance, hundreds of milliseconds, so the signal arrives at the G-node B on time. But here is the collision. The moment the grant reaches you and you apply that huge advance, the slot you are supposed to transmit in has already passed. The schedule is asking you to send a packet in the past. That is physically impossible. K-offset fixes it. It is a scheduling offset, broadcast per cell, that pushes every uplink timing relationship far enough into the future to absorb the entire round trip. Instead of transmit K slots later, it becomes transmit K plus K-offset slots later. And the rule is simple. K-offset has to be at least as large as the round-trip delay. The service link plus the common part. Set it right, and every uplink, the network schedules lands in a slot the phone can actually reach. Kmac is the quiet one, but it solves a real ambiguity. Remember, uplink timing is defined at the reference point, up near the satellite. But the G-node B, the thing actually issuing commands, sits on the ground, a feeder link away. So when the network activates something, a new configuration, a measurement, an uplink resource, there is a question. Take effect when, exactly? By the G-node B's clock, or by the timing reference up at the reference point? If the two disagree, the phone applies a command in a different slot than the network assumed, and things break. Kmac is the offset that closes that gap. It shifts the reference for these downlink-triggered actions so the G-node B and the phone agree on the precise moment a command becomes active. When the G-node B already sits at the reference point, Kmac simply isn't needed. One more moving target, literally, frequency. A satellite tearing across the sky drags every carrier with it. The Doppler shift. On a low Earth satellite, that shift can reach tens of kilohertz. more than enough to push your signal off its subcarriers and wreck reception. So NTN handles Doppler exactly the way it handled timing. It splits the problem at the reference point, the service link shift between your phone and the satellite. The phone pre-compensates itself. It already knows the satellite's velocity from ephemeris and its own position from GNSS, so it computes the relative motion and pre-corrects its transmit frequency. The feeder link shift between the satellite and the gateway is the network's job, corrected on the ground. Each side cancels the Doppler on its own segment, and the carriers line up. For geostationary orbit, the shift is small. For a fast, low-Earth pass, this is doing a lot of work. So here is the complete picture. Your phone computes the service link half of its timing advance from GNSS and ephemeris. The network supplies the common half in SIB19 with a drift term to extrapolate between updates. Koffset shifts the whole uplink schedule far enough into the future that the phone can actually meet it. Kmac aligns when commands take effect across the feeder link, and Doppler is pre-corrected on each segment, the same split, at the same reference point. All of it governed by a validity timer, so the moment the numbers go stale, the phone refreshes before it dares transmit. That is how a phone stays perfectly in sync with a satellite it can barely see. So far, we have kept the G-Node B safely on the ground, but what happens when we put it in orbit, when the satellite stops being a mirror and becomes the base station itself? That is regenerative NTN, and it is next. Subscribe to RANspace.